Okay, I'm going to run through this week 2 Excel sheet, which is labelled week 2 RVF, rapidly varied flow, specific energy calcs. We're going to look here in the first tab, which is labelled cubic solution, and we're going to look at methods for helping us solve the cubic equation. So this is not specifically about open channel flows, but in open channel flow, when we do energy calculations using a specific energy equation, we often end up with a cubic equation which we need to solve for the three roots. So a typical equation, generic cubic, will look like this. We've got a function that we rearrange so it's equal to 0. We have ay cubed plus by squared plus cy plus d. Now if it was a cubic, we could write our standard formula for two solutions for quadratic, but there is no such equation for a cubic, so we're going to do a numerical solution. So this is the cubic equation that we got from example 1. You'll see that in the slides. We've arranged this so there's 1 y cubed minus 1.18 y squared. There's no y, and there's a constant at the end of 0.204. Now I've written these numbers in these 3 cells labelled from A, B, C, D. There's slightly more decimals on the B and D, but don't worry, we could have used 1.18 or 2.204 in here. Now, first thing to do when we're trying to find a solution to a cubic is to try and find the range we're working in. Now, fortunately for the rivers, we know that we're between 0 and 5 or 10 metres. So we've got an already known range. But let's have a look at plotting this function first of all. Now I'm going to draw an ad hoc table here. I'm going to start with a column for y, column for the function. That's my y. So, typing the function in this cell C11. So it's a as a constant times the estimate value y cubed plus b as a constant times y squared plus, and we're going to use c, but there's no c, no y, c as a constant times y plus d as a constant. Okay, that's the function for value 0.02 when y equals 1. Now in this table I usually, so it's a bit flexible, I usually have a dy, so the increment I'm going to add onto the y. So how would I use that? In the cell below the first y I go one above the y above plus the dy value as a constant. And I can pull the function cell down, and I can drag those down somewhere. So numbers have got very big. We see that these numbers don't change size. So there's no solution in this range, but we can have a look at that in a moment. Let's just plot this. So we select the 2 columns, including the headers, and we'll go to Insert, and we'll go to the charts, choose Scatter with straight lines. Okay, there's a function of Fy. Okay, it's not very good. What we're interested in is where it crosses the x-axis and it doesn't cross the x-axis. So let's put 0 as the start value in here. We see that it crosses just below 0.6 and just below 0.1, but this is not very useful. We want to be focusing this graph on where it crosses the x-axis. And actually there'll be another solution that's negative. So just to get all the solutions in, let's go minus 2 as our start value. Okay, well it's now gone minus, we see it's a bit above minus 0.05, so I'm going to do minus 1 here. So you often have to do this trial and error, so it's going to just cross above 0.5. We'll see that these are way off, so let's try minus 0.5 in here. Okay, that's a lot better. We see that the line crosses at just above minus 0.5, just after 0.5 and just below 0.1. And we can see this in the table here. There's a change of sign in the function there between 0.3 and minus 0.3 and minus 0.4. There's a change of sign between 0.5 and 6. And there's a change of sign between 0.9 and 1. So that's where we're going to try and focus our efforts to get a solution, and maybe the initial value of any iteration will do. So let's do an iteration, and I'm going to do a secant calculation. We cannot calculate the 3 values all at once. We can only calculate the 3 solutions one at a time. Secant method will only calculate 1 solution at a time. I've got the secant equation written in the sheet for you. Let's move over and focus on that. So I've got in the blue cells here 2 estimates of the secant value, 0.8 and 1, and that's sort of traversing where we think that solution may be near 1. We don't have to choose these 2 numbers. We'll have a look at choosing other ones. Handily, we can just copy those first 2 function values into there, and we see that the solution is indeed between 0.8 and 1. But the next estimate, we need to then use this secant formula, and this is it. We've done it before. So it's the last y value minus the function of the last value times 2 brackets the last y value minus second last y value divided by the last function value minus the second last function value, double bracket, there's our next estimate, and we get that function value of minus 0.01 for that. So let's highlight those 2 and drag them down a bit. Okay, well we'll see that this has converged very quickly to 0.9586. Probably too accurate then. Let's sort out our decimals. Actually, I've got one more than the number of millimetres, just so we can see the difference. So, 0.9586 is the solution, so I'm going to put our y values, y solutions 0.9 of 86 is 1. The other one, the next one along is between 0.5 and 0.7, so let's try that. 0.5 and 0.7. Okay, it's zoomed in the secant method and got 0.5852. 0.5852. And the value that's negative, we're going to solve it for this value. We won't need it when we're doing open channel hydraulic questions, but let's see, well it's between 0.5, minus 0.5 and 0, so if I put minus 0.5 and 0, okay, that one's worked, taken a bit longer to get there, but it's minus 0.3634, minus 0.3634. Okay. Now quite often we know that we only want to solve for the highest value. So that might be the first thing you're going to do, as long as that's higher than the critical depth, if you know the critical depth. But this is a method to help us identify which are the, approximately, first of all approximately from the graph, what are the values, and then use a iterative method to zoom in. Now later on I'm going to show you a secant cubic solver, which is this function, which I've written in Visual Basic. I'm not going to do it straight away because it's a little bit more confusing and distracting. And this one actually gives you the three values. It does it via three iterative methods. And the second one called get highest cubic depth, and we'll just get the highest one of those three. Okay, we'll see those a little bit later in the sessions. Okay, thank you.